Hey everyone, I'm Chris McCormick. In this video, I wanted to take my usual illustration-based explanation for how self-attention works and map it back to the original equations for self-attention, the mathematical equations. So what I'll be doing is going through my illustrations again, but this time showing the equations alongside and pointing out the connection between the two. So this is a sped up clip of from later in the video to give you a sense of what I'm talking about there. These equations come from the paper for the original transformer, Attention is All You Need, back in 2017. They're on pages 4 and 5 of that paper. And you'll find these equations used elsewhere where people are using self-attention as a building block in some other model. And here they are, pulled out. There's kind of three main components and then all the variable definitions down here. So we'll be starting with the projections onto the query and key spaces. And then we'll look at the calculation of the attention scores. And then the projection onto the value space and the application of the scores to the value vectors. And then finally, the recombination of all of the heads into a single attention output. And as we go, we'll look at the variable definitions and their dimensions. So there's a couple concepts that I want to go over about attention and what it's really about. It's going to help me define some terms that'll be useful throughout the rest of this, and I think it's a good insight in general here. So attention really happens between a set of input vectors and a set of target vectors. And the idea is that we're trying to select information from the targets that we want to incorporate back into the inputs. So attention is the process of figuring out which of these targets to pull from, how much information to pull from, what information to pull from it. And ultimately what we'll get is for each input vector, we'll have a vector that stores all of the information that we pulled out of those targets. And then in practice, what we do is we have what we call a residual connection, where the output of attention is actually just this kind of like adjustment vector, where we'll take the original input and add the selected information to it. And then that's what we use, that's what we take as our final updated embedding at the end. So part of the reason I wanted to define it in terms of these terms, input and targets, or context is maybe another word, is that self-attention has a lot of uses outside of just models like BERT and GPT-2. So in BERT, we call it self-attention because we're basically, for every word in the sentence I like to draw, we're attending to every other word in the sentence. So it's this very self-referential thing. But the input and the targets don't have to be the same thing. So for example, if we're doing translation, then the Spanish word to draw, dibujar, we could attend back from the Spanish word to the original English words to pull in information from those words to update dibujar with. Or maybe an even more interesting example, we can combine text and image data using attention. So we could attend to different image features. So as long as they're stored as vectors, we can attend to them. The targets and the input don't have to be really the same kind of data. They don't have to be the same vector length either. For transformer models like BERT and GPT-2, we know that there's not just a single attention unit at work, right? There's actually a lot of them. So the base size of those models, they each have 12 layers, and each layer has 12 self-attention units in it. So 12 layers times 12 heads, there's actually 144 different self-attention units in BERT base or in GPT-2, the base size. And again, the job of self-attention is to look for information in the targets that we want to incorporate in the input. And each head is looking for a particular relationship between input and target. In order to detect those relationships, the first thing that we do is make some projections. So we're going to take our inputs and we're going to multiply them against the query projection matrix. And that will give us our inputs in the query space. And then we'll do the same for our targets. We'll multiply the targets against the key projection matrix, and then that'll give us a representation of our targets in the key space. So really what we're doing there with those projections is that we're trying to pull out features from the input and features from the targets that are going to help us to detect the relationship that this particular head is looking for. And also I think it's worth noting that usually when we do any kind of feature extraction, the number of dimensions goes down significantly. So we're going from a length 768 embedding down to length 64 in the query and key spaces. A quick sidebar here. If you're unfamiliar with the concepts of word embeddings and projections, or if what you're really after is a complete picture of these large language transformer models, then check out my membership site. I recently published a course on decoder-based transformers like GPT-3, and I think that's a great place to start for getting an understanding of these NLP transformers. And then from there, there's lots of additional tutorials on related topics and example code that you'll have access to as a member. And if you're a student or in another part of the world where you really can't afford reasonably my content, don't let that stop you. I have a student membership application. Fill it out. We'll definitely get it to a price that works for you so that the price tag doesn't get in the way of your education. All right, let's get back to it. Since the goal here is to understand the equations this time around, let's label each of these matrices with the variable name that they're given in those equations. So first of all, the projection matrices are labeled with the letter W, and this is the query projection matrix, and then this is the key projection matrix, K. And then the output here, the projections, we call Q and K. And because we have different heads, we have to number the heads. So this is actually the projection matrix for head I, and these are the inputs in query space according to head I. So here as well. And then the dimensions, since these are listed in the paper as well. So the dimensions for the query projection matrix for head I, it's a matrix which is a member of, R is like real valued numbers, and I think this is like a member of the domain. Some weird mathematical terminology, but D model is the length of the embeddings, so 768 for BERT base and GPT-2 base. And then dk is the dimension of the key vectors, and the query and the keys need to have a matching vector length. So dk has got to be equal to dq if you wanted to define that, and in this case they're both 64. And then one other variable I'm going to, or a couple of variables I guess, that I'm going to add here that these are my own convention, but everything else is going to be, corresponding to the official equations. But I'm going to call the inputs x, and the targets, I'm going to use the variable c, matrix letter c. Using t felt a little weird. C to me stands for context, maybe another term you could use instead of targets. So you can write some equations here based on that. So Qi is equal to x times the projection matrix, the query projection matrix for head I, and the keys for head I are given by the target vectors multiplied by projection matrix as well. So these are the two things that we need in order to calculate the attention scores. So let's move on to the next step. Okay, now we can use those queries and keys to calculate the actual attention scores. So up here is the equation for attention. And in this slide, we're just going to look at what we do with the queries and keys. We're not going to look at the values yet. And so we'll be looking at this portion of the equation, everything except for that v there. And the first step for calculating the scores is to perform this matrix multiplication. So we'll take the queries, this is the matrix Q, and we'll take the keys, which is the matrix K, but transposed, and we will multiply those two together to get, these cancel out, and we'll get these four values, one for each pair of the input and targets. And then there's this additional step here that I tend to omit because it's a small detail, but we're going to divide each of these values by 8, since dk dimension of the keys is 64. So square root of that is 8. And the reason they give for this in the paper is that these dot products, they think, can get fairly large. And then when those are large, that pushes into a region of the softmax function where the gradients can get really small, and that's bad. So we just scale it all down. I don't think it affects the relative values or the relative magnitudes of the values. So I don't think there's any harm in doing it, and it seems to help with the training. So that's what they do with that term. And so once we've divided by 8, we've got these four values that you could call these the raw attention scores or the attention values. In order to get the actual scores, we just need to apply the softmax function, this step. So we do that across all four values, and we get the attention scores. And the softmax is, I'll write it over here, uses the exponential function. So what we do is we apply the exponential function to each of these four values, and then we sum up those results, and that gives us our denominator here. And then for each value, we apply the exponential function and divide it by that sum. And that's what gives us our final scores. And those will all be between 0 and 1, and they'll all sum to 1.0. All right. And then one final thing to note about this. So we're looking at the attention scores for a single head, right? So this is actually the queries for head I and the keys for head I. And so you might think that in order to do this for all 12 heads at once, that we just kind of stack the keys and the queries together and make this 768. 12 times 64 is 768. But that doesn't actually work. If we were to do that, then these cancel out, and we would still only get 4 score values. But what we need is 4 score values for each of the 12 heads. So what you'll see in the code is that this is actually done with a tensor that's 12 by 1 by 64, 12 by 64 by 4, so that we get 12 sets of the 4 values. We just looked at how a head uses the attention score mechanism to select which targets, if any, match what it's looking for. But we know that the other role of the head is to actually extract information from those targets that we want to incorporate back into our input embedding. So that's what this next step is about. Just like we had the projections into the query and key spaces, we're going to make a third projection here into the value space. So this time the purpose of the projection is to extract from each of the target vectors the information that this head is looking for. And we do this for all of the target vectors, even though we're not actually going to take information from most of them because the head is looking for something specific, right? Now we can combine those two pieces of information, the selection of targets and the information extracted from those targets. And the way we do that is by taking the dot product between the attention scores and the value vectors. And what's happening when we do that dot product is that we'll take, for example, the attention score for the word I, and we multiply that value against every feature in the value vector for I. And then we do the same we take the score for like, multiply that value against every value in the value vector for like, and then we sum all of those together to produce this single weighted average of all of those vectors. And again, because many of the words in your input aren't going to be relevant to what this head is looking for, a lot of these attention scores will be 0 or close to 0, and they won't contribute. The value vectors for those words won't contribute much or at all to the weighted average at the end. All right, let's make sure we tie this back to the original equations like we said we would. So we're talking about this step right here, where this entire term was all about calculating the scores, and then we're just multiplying the resulting scores against the value vectors. And let's label these matrices again. So these are our target vectors, calling this C. And then we've got the projection matrix for the value space. So we use W for those, and this one's the value space. And then again, there's one of these for each of the 12 heads in this example. So we'll denote the head by I. And then these are the value vectors, call those V. And then the dimensions for this weight matrix are interesting because we've got, again, the model dimension, the embedding size, which is 768. But then, whereas previously we were using DK for both the query and key vectors, here we can use a different value. So the query and key spaces needed to be the same length because we were taking the dot product between the queries and the keys. But we'll see that with the values, they don't interact with the queries and keys. So they could be any length that we want, but 64 is what's used in all the models I'm familiar with. So they're all the same length. With that, we've got the information from the target vectors, and we want to add that now to the input embedding. However, we are down in the value space at length 64. And if we want to add this information back into the input embedding, we need to get back up to length 768. So we've got one final matrix multiplication step here. We have what you could think of as a value space to input space projection matrix, where we're going to take that vector from the previous slide and multiply it against, let's say this is so W, they call it like the output matrix. They use O as the letter. And in this case, I'm doing it for a single head. And we're taking the transpose of this matrix in order to multiply this vector by it. So when we've done that, what we have is a vector which is the combined information from all of the targets, and it's now in the input space instead of the value space. So almost there, because one aspect that we haven't covered yet is that we've got these 12 heads. So how do we combine the information from those 12 different heads? So we could do this 12 times. We could have 12 separate value to input projection matrices to project each of the heads results back to the input space and then sum those together. But we can kind of add on to that and also do a weighted combination of the outputs of the different heads. So we can decide how much influence to give each of the heads. So the way we do that is we actually will take the output from each of the heads. So these are all length 64, and there's 12 heads. And we concatenate those into one length 768 vector. And then that output matrix, we don't actually have one per head. We instead just have a single output matrix that's 768 by 768. And it's able to serve both roles. So you could picture taking this vector, turning it 90 degrees, multiplying it against the first column of this. And what that does is the weights in this projection matrix will give different weight to each of the values from all the heads and sum them up to a single value. Yeah, so that's both projecting from the value space back to the input space and then also doing sort of a weighted combination of the outputs of the heads. This step of the process is captured in actually the first line of the equation, where we have the multi-headed attention function, and it shows that we are going to concatenate the 12 different heads. H is the number of heads. Not sure if we've seen that before, but it's important. And then once they're concatenated, we multiply them by WO. And as for the size, dV can be a different value, but this matrix, the recombination matrix, needs to have a number of rows equal to the number of heads times the length of the value vectors. So again, there's this concept of the residual connection, which I wanted to include because it definitely changes the interpretation of what's output by self-attention. The residual connection is not included in those equations, but you can see it here in the original illustrations for the transformer. So we have our inputs going into multi-head attention, but then we also have this line where we're taking the inputs and bringing them up to the output of multi-head attention. So we're taking the output and we are adding the output to our input vectors. Then we're also doing this step of layer normalization, but that one is an important step, but it doesn't have an impact on the interpretation of the self-attention output, so it didn't feel as important to cover here. But again, what all that residual connection really is that we'll take our final selected information vector containing the information from the targets that we've extracted, and we're going to add that to our input embedding so that now we have our final enriched embedding for the word draw, where we've enriched it with additional information from those targets. All right, so let's review the equations one more time. Hopefully we can look at these and feel pretty comfortable with them now. So one source of confusion, I think, in these equations is that they do use Q, K, and V in multiple ways. Here they're using it as what vectors do you want to perform attention on, which is the targets and the context, or the inputs and the targets. And then we also use them as the query vectors and the key vectors and the value vectors, so that the input vectors projected into those spaces. So I think it helps to think instead, queries are going to be X, our inputs, and keys will be our targets, C, and values will also be targets, C. So then we can use the letters Q, K, and V just for the projected versions. So Q equals X times WIQ, for example. And we do that for all 12 heads. So we make those projections, pass the projections down, projected embeddings. Run attention, calculate the attention scores, and then use those scores to select information from the target vectors. And we do that for each of the 12 heads. And then the final step is to concatenate all 12 and multiply it by the recombination matrix, which will give us a length 768, a D model length vector. We already looked at these matrix dimensions. This line here is the choice that the transformer, the authors of the original transformer made. So it's not required that these things be true, but this is their choice. So the length of the keys they chose to make the same as the length of the value vectors. And then they made both of those equal to the length of the model divided by the number of heads. There we go. So hopefully now these equations make sense, feel relatively comfortable to look at, and maybe you've picked up some additional insights too into how self-attention can be used in a more general way beyond just these NLP models. Thanks, guys.